Okay, the synthesis review, the first reactions that would produce carboxylic acid is oxidation. We talked about oxidation of primary alcohol using PCC to go to aldehyde. But if you use strong oxidizing agent like chromic acid or permanganate, the oxidation would continue and it will go to all the way to carboxylic acid. So using primary alcohol with a strong oxidizing agent would yield carboxylic acid. That's one method to prepare carboxylic acid via oxidation. And for the oxidation, your reactant can either be aldehyde or primary alcohol. If it's primary alcohol, you need a strong oxidizing agent to change to alcohol. If it's aldehyde, you also need a strong oxidizing agent to change to carboxylic acid. Second method, this is again a review, is that from reactions of alkenes, if you remember, if you had cold dilute permanganate, it would yield, it would only break the pi bond. But if you are using concentrated permanganate or hot permanganate, concentrated permanganate with heat, is going to break both sigma bond and pi bond. So it depends on the permanganate that you are using. If it's hot permanganate, it will change to carboxylic acid. Now, if the hot permanganate that you are using, if you don't have hydrogen attached to the carbon carrying the double bond, is not going to go to carboxylic acid. It will change to ketone. So you have to be careful which alkene you are using. So let's say you want to make a carboxylic acid. Okay, say you want to make a carboxylic acid that is 4 carbon. You want to make this carboxylic acid. One of the methods, oh, can you give me the first method? What can you use to make this 4 carbon carboxylic acid? What reaction? Give me either the name or just tell me how many carbon, what functional group I should use. This way, hopefully you remember for longer. What should I use as a reactant? I'm trying to make carboxylic acid based on what you have learned from previous reactions or what we talked today. What should I start with? Any response? One of the methods would be to use primary alcohol. And with the primary alcohol, you can use a strong oxidizing agent, H2SO4, with sodium dichromate. This would take the primary alcohol to carboxylic acid. Another method would be to use aldehyde with 4 carbon. If you have aldehyde with 4 carbon and you can use hot permanganate, chromic acid, or sodium dichromate with sulfuric acid, basically this combination, it gives you chromic acid. It would oxidize aldehyde to carboxylic acid. So all of these we're trying to prepare we're trying to prepare carboxylic acid. What happens if you use PCC here? If you add PCC to aldehyde, there would be no reaction, okay? So we can't use PCC. We have to use a strong oxidizing agent in order to go to carboxylic acid. With primary alcohol, if you use PCC, it would change to 4-carbon aldehyde. It would change to 4-carbon aldehyde, and it does not go to carboxylic acid. So it doesn't give us the carboxylic acid. And if you have aldehyde, you have to use a strong oxidizing agent in order to go to carboxylic acid. With the PCC, which is a mild oxidizing agent, if you start with primary alcohol, you end up with aldehyde. If you use secondary alcohol, you end up with ketone, and the reaction stops there. But if you have primary alcohol, use PCC to go to aldehyde, then you can use a strong oxidizing agent in order to change that to carboxylic acid, because PCC does not oxidize aldehyde. It's not strong enough to oxidize aldehyde. Third method, we want to do oxidative cleavage of alkene. So what happens if I use alkene, like 1-pentene? If I use 1-pentene, then I do oxidative cleavage. One side is going to give me 4-carbon carboxylic acid, because I have to use a strong oxidizing agent. The other side of the carbon chain is going to give me like 1-carbon product. It can give you like an aldehyde or formic acid. It doesn't give me what I need. This is the wanted product that we want to make. The best method would be to get a symmetrical alkene, that 4-carbon on each side. Now, both sides is going to give me carboxylic acid. So basically, I'm going to end up with 2 molecules of carboxylic acid if I use proper reagent. Okay? If I use proper reagent, like that would be permanganate, I must apply heat, and it has to be either acidic or basic condition. Okay? In acidic condition, so I have to use hot permanganate in acidic condition in order to change this to carboxylic acid. And on purpose, I used 8-carbon alkene with the carbon double bond being between carbon number 4 and 5. So if it cleaves through the carbon-carbon double bond, it would give me 2 molecules of that. Then I don't have to be worried about purification and other problems. Okay, so those are like 3 methods. 4. You remember anything from organic 1, getting carboxylic acid as a product, starting with other compounds? If I have a nitrile, if you hydrolyze nitrile, H2O in acidic solution, when you hydrolyze it, it's going to give me carboxylic acid. Nitrile is an acid derivative, so if you hydrolyze, it would change to carboxylic acid. If you have other carboxylic acid derivatives, let's say you have a acid chloride, okay, that's a COCl. If you have acid chloride and you hydrolyze it, in general, any acid derivative like ester, like acid chloride, like acid anhydride, if you hydrolyze, it would give you carboxylic acid. The other product, basically, this is like a substitution reaction. OH would replace the Cl, and then the hydrogen from water, it goes with HCl. It gives like byproduct of HCl. Okay? But we don't worry about the byproducts at this point. We just need to know the reagent. It's very important to know proper reagent and what is the product. Now, other acid derivatives as a result of hydrolysis would also give the same product. So because it's kind of repeating, I don't want to repeat the exact same reactions. But if you have, for example, if you have ester with 4 carbon and you hydrolyze this in acidic solution, it would give you the same product. So the product would be the same. So you have different methods to prepare carboxylic acid, from the oxidation or from substitution. This is like substitution. This is like hydrolysis or oxidative cleavage. For the oxidative cleavage, you must make sure that you have a hydrogen here. So there must be a hydrogen. So you cannot have like 3R or 4R and expect carboxylic acid. If you had 3R or 4R, then that would actually, if you had a 3R or 4R, okay, trying to move to the next. If you have 3R or 4R alkene, let's say you have double bond here, and then you have C, like this. One side of the molecule, as a result of oxidative cleavage, one side of the molecule is going to give you carboxylic acid. The other one would be ketone. If you have 4R, and the oxidative cleavage was KMnO4, heat and acid. Okay. H3O plus, because you follow by hydrolysis, and or ozonolysis followed by hydrolysis, either one of them. This one, oxidative cleavage, yes, of course, is going to take oxidative cleavage, but you don't have any hydrogen here. And if you don't have any hydrogen, the product is going to be ketone rather than, your product is going to be ketone rather than carboxylic acid. So you have to be careful if you are choosing the alkene. You have to choose proper alkene for the hydrolysis or for the oxidative cleavage. Questions? For preparation of the carboxylic acid using Grignard reagent. Okay. So that's another method. So we had 6 methods already, or maybe 7. We had 6 methods since I numbered. 7th method, you can use a Grignard reagent. MGBR, you all know already what MGBR is. MGBR is like a R negative, Mg positive, Br. That's the general formula. So we know that this side of the molecule is a strong nucleophile. Plus CO2. That is going to give us, followed by hydrolysis. Okay, so first you have to add the CO2 and then hydrolyze it. The product is going to be carboxylic acid. So basically, if you look at the mechanism for this reaction, the negative charge from the Grignard reaction on the carbon is going to make this a strong nucleophile. So this strong nucleophile is going to attack the carbon from carbon dioxide. So we would have an attack here. Because there's no leaving group here, there is no leaving group because oxygen is not good leaving group, hydrogen is not good leaving group, alkyl is not good leaving group, then pi bond will break over the oxygen. There is a new carbon-carbon bond because this is like partially positive carbon because oxygens are highly electronegative and they pull electrons. So carbon is partially positive carbon. The pi bond breaks over one of the oxygens because you only need one of these pi bonds to break. Why do you need only one pi bond to break? And the reason for the pi bond is breaking is because carbon has 4 bonds already in carbon dioxide. And that's the maximum number of bonds that carbon can have. Carbon cannot have 5 bonds. When the nucleophile comes and attacks and forms a new bond, you are forcing 5th bond to this poor carbon, and that's not possible, and it's going to make the carbon very unstable. So the solution to that would be the weakest bond or one of the weakest bonds should break. We know we have a pi bond and sigma bond on the left side, and we know that we have a pi bond, 1 pi and 1 sigma on the right side and 1 pi, 1 sigma on the left side. One of these pi bond has to break, and only one needs to break because carbon cannot have 3 bonds either. So it has to be 4 bond only. And it would give negative charge to oxygen. So you have your 3 carbon that is coming from Grignard, and then you have 1 carbon that is coming from carbon dioxide. You have double bond oxygen, one of them stays, and the other one is going to be negative charge, the other oxygen, because the pi bond break over that oxygen. And the next step, when you hydrolyze, because Grignard should follow by hydrolysis, basically you are going to protonate that alkoxide that forms. And when you protonate, you get the as a product, you would get the carboxylic acid with 4 carbon. Any questions so far? So Grignard plus CO2 would give you carboxylic acid. Okay, carboxylic acid with addition of 1 carbon. So if you want to make carboxylic acid with 4 carbon, your Grignard should carry 3 carbon only, because you are adding CO2, and the CO2 is going to give you the next carbon, the 4th carbon. An example, you are given propyl bromide. Okay, start with propyl bromide and prepare. The examples are very close. Prepare using 2 different methods. Okay, can you tell me one? What would be the first method? You have alkyl bromide or propyl bromide, and you want to get butanoic acid. What would you do? What method you would use? Tell me your steps. I need everyone to participate. So please tell me, what would you use to prepare the 4-carbon acid. You have 3-carbon halide and you want to make 4-carbon acid. You will get 1 extra point on the next exam if you give both you give 2 correct formula or 2 correct method to prepare it. And no partial credit on that. You must give both of them correct name because we already talked about the reactions. Okay. As soon as my time shows 6:25, I will start. No attempt even? Can I add CO2 to propyl bromide? To propyl bromide, can I add CO2? Would it react with CO2? So what should be done? Okay. Going to start with the propyl bromide. Add magnesium to change this one to Grignard reaction. Then to the Grignard reaction or Grignard reagent, add CO2. You will get carboxylate, then you hydrolyze it. This is one method. Method 2, okay, so you must add CO2 to Grignard, not to alkyl halide. Method 2, you would use your propyl bromide, because the difference between propyl bromide and carboxylic acid is 1 carbon. You must add a carbon. Okay. You would change the alkyl bromide to do a substitution reaction like SN2 type reaction plus Na plus Cn. That's the sodium cyanide. This is SN2 type reaction. You have your nucleophile that is going to, the Cn with the negative charge is going to replace the Br. Br is going to leave, and you end up with 4-carbon nitrile. When you have your 4-carbon nitrile, we just said in the previous slide that if you have 4-carbon nitrile, then you can do hydrolysis of 4-carbon nitrile to change that to 4-carbon carboxylic acid. Okay, so these are 2 methods. These are not the only 2 methods. Because after you make Grignard reaction, you can use different routes. After you make your Grignard reaction, so we already know how to make Grignard reaction already. Then you can add formaldehyde. What happens if you add formaldehyde plus the Grignard reaction? You would get primary alcohol with addition of 1 carbon. It's the RX or alkyl halide plus the formaldehyde or Grignard plus formaldehyde. It gives you primary alcohol with addition of 1 extra carbon. So basically you're adding this carbon. Okay. And then to this primary alcohol, if you add sodium dichromate, it would change to carboxylic acid. It's end of the semester. I mean, at this point, you should be able to do synthesis using prior knowledge, using all the reagents that you have used in the past. And it's not a lot if I expect you to respond and know how to go from like a certain reactant to the product. Okay, let's see other methods. So we already talked about several, like 7, 8 different methods. We talked about the Grignard plus CO2. For aromatic alcohols, you can do the oxidation of a side chain. For oxidation side chain, you have to be careful, and in order to do oxidation, there must be a benzylic hydrogen. So let's say if you have toluene with KMNO4, it would give you benzoic acid. Because you have the side chain would change to it. If you have ethyl benzene, of course, heat and hydroxide, okay? Heat and hydroxide. It would change to if you have isopropyl group, with permanganate, it would change to benzoic acid. So side chain oxidation, as long as you have benzylic hydrogen, that's benzylic hydrogen, and this is benzylic hydrogen. If there is no benzylic hydrogen, there would be no reaction. So if you have T-butyl group attached here, plus the KMNO4, there would be no reaction. You must have benzylic hydrogen, that is the condition. But regardless of the size of the alkyl chain, as long as you have benzylic hydrogen, the product is going to be benzoic acid. So that's like aromatic or side chain of aromatic ring, oxidation of side chain of aromatic ring, which is going to produce benzoic acid. Hydrolysis of nitriles, we talked about hydrolysis of nitriles already. So if you have alkyl halide and you can do substitution reactions, SN2 type reaction, CN can replace the leaving group of Br. It adds up 1 carbon. When you do hydrolysis, nitrogen would leave, but the carbon from the CN triple bond would change to COOH. So be careful, it's adding a carbon. Okay, so keep that in mind. It's going to add the add additional carbon. So if you have here just one carbon attached to benzene ring, and carboxylic acid that you get has 2 carbon attached to the benzene ring. That extra carbon is coming from the nitrile you have. What are acid derivatives? Acid derivatives are those compounds that if you hydrolyze them, they go back to carboxylic acid. Example of acid derivatives, you have carboxylic acid, which is carboxylic acid, acyl halide. Like if you replace the OH with halide, that's one acid derivative. You replace the OH with acetate, with carboxylate, that gives you acid anhydride. So you have your carboxylic acid derivative. With the OR, basically, it gives you ester, and replacing OH with NH2, it gives you amide. For each of these compounds, you need to know how to prepare these compounds and what are some of the, naming and some properties of those acid derivatives as well. Any questions about preparation of carboxylic acid? Review. Basically, they were all reviewed. There was no new reaction that we covered. Okay. To prepare esters, you can mix acid plus alcohol, or acid derivative plus alcohol. So if you were going to make ester, you can add carboxylic acid plus ester. You have this reaction here, general reaction. It's a substitution type reaction. Alcohol is a nucleophile, okay? Alcohol is going to be the nucleophile. OH is a leaving group. And if you look at this previous slide, anything that has the green color, those are leaving group, basically. It adds a specific class to the carboxylic acid derivative, but at the same time, they count as the leaving group in substitution type reaction. So in this reaction, OH is leaving group and the alcohol is a nucleophile. Is your nucleophile strong nucleophile or weak nucleophile? Is alcohol strong or weak nucleophile? Alcohol is just like water. Is water a strong nucleophile or weak nucleophile? You know the definition for nucleophile? Nucleophile looks for nucleus or positive charge. So if it's already stable and neutral, a neutral nucleophile cannot be very strong nucleophile. So alcohol is weak nucleophile. What about OH? Is OH good leaving group or weak leaving group? Or bad leaving group? OH, is it good leaving group or bad leaving group? A leaving group is going to be a strong leaving group if after leaving is going to be stable on its own. If OH leaves, so hydroxide is very reactive, is not stable, is going to be classified as not a good leaving group. So OH is not good leaving group. And since the OH is not good leaving group, and alcohol is not strong, nucleophile, this is a weak nucleophile. So alcohol is weak nucleophile, OH is not good leaving group. How can we do the substitution reaction? We have to have a catalyst. So acid is going to be used as a catalyst. So what's going to do is going to protonate the OH and changes to better leaving group. Then leaving group leaves, and then OR or RO is going to replace the OH. And that's when we have ester, a new functional group called ester. This reaction is a double side, double arrow. That means it's reversible reaction. Means that if you have ester plus water in acidic solution, it can give you carboxylic acid. I use this as a preparation for carboxylic acid because ester plus the water in presence of acid, it can hydrolyze and it gives you carboxylic acid. There's an example of ethanoic acid or acetic acid with ethanol that gives you ester with 4 carbon. 2 carbon is coming from acid and 2 carbon is coming from alcohol. Condensation, this is like esterification, this type of condensation reaction. You start with acid and alcohol, you end up with one molecule called ester. But we know that to make ester, it's coming from 2 separate molecules. One side of the molecule is coming from carboxylic acid and the other side of the molecule is coming from alcohol. So we have the two combined, we combine the two together as the product. We have ester. If we have like phtalic acid, this is the dicarboxylic acid, 2 carboxylic functional group. With methanol, then you have to use excess of methanol because you have 2 carboxylic acid. Use 2 moles of alcohol, then you get dimethyl phthalate, or we get the ester that OH is replaced by OCH3, both of them. Again, is a double arrow. That means that this reaction is reversible. So basically to dimethyl phthalate, if you add water and acid as a catalyst, it can go back to phthalic acid and methanol. It would break down. The reactions are all reversible. Any questions about esterification of the carboxylic acid or Fischer esterification when you have ester plus alcohol that gives you ester? Carboxylic acid plus alcohol, it gives you ester. Well, it's not just the carboxylic acid. It could be any acid derivative. Any of the acid derivative plus alcohol can give you ester. So if you have acid plus alcohol, it would give you ester. See, one side of the molecule, okay, this side of the acid and this part of the alcohol. You make ester. So it's acid plus alcohol that gives you ester. Preparation of ester. 2, you can have acid chloride, that's acid derivative, plus CH3OH, that would give you COOCH3. Does this reaction, the second reaction, does it need a catalyst? If you compare the second reaction to the first reaction we already talked about. OH is not a good leaving group and alcohol is not a very strong nucleophile, so you do need a catalyst. For second reaction, the story changes because Cl is a good leaving group and you don't need a catalyst. So the weak nucleophile, even alcohol, can replace the Cl, and you get ester as a product. So alcohol, and this is acid chloride. Acid chloride. 3. If you have acid anhydride, that's another acid derivative. Acid anhydride. You notice the functional group for acid anhydride is CO double bond, O, CO double bond. That's acid anhydride. Basically, 2 moles of acid have lost the water and changed to acid anhydride. If you add water, you add H to the oxygen and OH to this carbon, you end up with 2 molecules of carboxylic acid. So acid anhydride plus alcohol, it gives you S. And the other side, because it's identical, is going to give the same. So we get 2 molecules of ester. And in this case, you also use alcohol plus acid anhydride. You see the alcohol kind of stays the same. So carboxylic acid or any acid derivative plus alcohol, that gives you ester. Even ester plus alcohol, it can give you ester. This is ester plus alcohol. It gives you ester. Ester plus alcohol gives you ester. You must use catalyst in this case also. This type of reaction, this esterification type reaction, is called transesterification, because all you do, you change the alkyl size. Instead of the etoxide, you have metoxide. Instead of OCH2CH3, you have OCH3, and that means you are changing the alkyl group from the ester, and the reaction is called transesterification. One ester changes to another ester. This is like preparation of ester. So for preparation of carboxylic acid, we had like 7, 8 different methods. For preparation of ester, basically, you can say one statement is carboxylic acid or any acid derivative plus alcohol, it gives you ester. Even ester plus alcohol gives you ester or trans ester, a new ester with different number of carbons. Questions? We have another reaction that we can make ester is carboxylic acid plus the diazomethane. In this reaction, you have carboxylic acid plus the diazomethane. In this reaction, basically the CH2 is going to replace hydrogen. Okay. You don't worry about the mechanism for this reaction, but just learn that diazomethane with the carboxylic acid, it can replace the hydrogen. Methyl group can replace the hydrogen, and it can give you methyl ester. It's just for methyl ester. In the mechanism, it shows like internal rearrangement and all that. But since there are a lot of reactions in this chapter, I would go more concentrate on the reactant, reagent, product, but you need to know plenty of different reagents, that how to convert from one acid or acid derivative to another acid or acid derivative, or how to prepare each of the acid derivatives based on the reactant, reagent, and product. And next, these are acid derivatives. Amide is one acid derivative. Also, amide, the functional group for amide, it's R, or if I use the alkyl group, CON. Okay, this part of the molecule is going to make the amide functional group. So if you have carbon attached to NH2, this is amine. Okay, carbon attached to CN double bond, if it carries CN double bond, that was imine. We looked at it last chapter. That's amine. If you have CO double bond, that could be aldehyde or ketone. But if the carbon that carries the nitrogen also carries a CO double bond, the name is going to change to amide. Okay, so we have amide. How do you prepare amide? To prepare amide, you must use carboxylic acid or acid derivative plus either ammonia or other amines. And I'm going to use, again, examples for preparation of the amide. So in this example, just like formation of ester, we can start with the carboxylic acid. So we have COOH plus ammonia, NH3. It's going to give me the carbons would stay. This is substitution reaction. When you are starting with in the carboxylic acid derivatives, the reactions or in preparation, you have like a substitution reaction. So you have a nucleophile, that's nucleophile, and this is the leaving group. So you have your leaving group. If the reaction, if the leaving group is not good leaving group or the nucleophile is not strong nucleophile, you would need catalyst. If leaving group is the good leaving group, you don't need a catalyst. So one pattern works, is not a mechanism, is not written in any books, and it does work all the time, is that hydrogen from nucleophile, H from nucleophile with leaving group leaves as byproduct. The rest of the nucleophile would form bond with the carbonyl carbon. So rest of nucleophile forms bond with carbonyl, with the CO double bond. So we looked at the leaving groups already, and I showed you the ones that they were colored. It's the leaving group. So OH is leaving group, and this is the nucleophile. Hydrogen from nucleophile with OH, it would give me byproduct. So byproduct of H2O, that's a byproduct. The rest of the nucleophile, what is left after the H2O, and after you remove hydrogen, is going to be NH2, is going to attach to the carbonyl group, and that gives you the product. So that's formation of this amide. Now, if you use, that's one method of preparation of amide. If you use primary amine, what's going to happen with the primary amine? I'm going to use the same carboxylic acid, And instead of ammonia, I use primary amine like a CH3NH2. This is a primary amine. The primary amine, can you use this pattern and tell me if you can get a product here? What would be the product? Or what's the byproduct? Can you tell me what's the byproduct? What's the byproduct here for reaction 2? Just follow that pattern. It's not the mechanism, but it works. Okay, if you cannot read, hydrogen from nucleophile with leaving group leaves as byproduct. So what would be the byproduct? Yes, the question is, what is the leaving group here? We already identified the leaving group. For carboxylic acid is going to be OH. Hydrogen from leaving group, okay? Hydrogen from this NH2 with the leaving group is going to give us H2O as the byproduct. The rest of the molecule, so from the, the nitrogen, because it has the pair of electron, or the nucleophile is the nitrogen, is going to form bond with the carbonyl group, and from the carboxylic acid, so the product is going to be CCCO NH, because I have NH2 now, it's going to end up with NH and CH3. This is also amide because I have CO double bond attached to nitrogen. Nitrogen for this compound is attached only 1 carbon. In this case, nitrogen is attached to 2 carbon. So this one, the first product is a primary amide. So this one is a primary amide. Second one, this one is called a secondary amide. Secondary amide. See, it's kind of a step up. You start with carboxylic acid and ammonia. You start with carboxylic acid and ammonia, you end up with primary amide. You start with carboxylic acid and a primary amine, you end up with secondary amide. And if we follow the same pattern, and you go to carboxylic acid with a secondary amine. What is a secondary amine? Is the amine that has 2 CN bond. So it's going to be like a CH3, 2 NH. So secondary amine is like NH attached to 2 methyl group. It's called a secondary amine. This is a secondary amine. Carboxylic acid plus a secondary amine is going to give you product. The product is going to be amide. And if you follow this pattern, I want you to just look at the pattern, read the pattern, and tell me what is the byproduct. Based on the pattern, what is the byproduct? Response for byproduct? Hydrogen from nucleophile. What's your nucleophile? Is it OH or the amine? With leaving group, what is the leaving group? Is the leaving group the amine or the OH? OH is the leaving group and amine is the nucleophile. A hydrogen is the only hydrogen that we have here. With the leaving group would give us the byproduct. So we have H2O as a byproduct. the rest of this nucleophile is going to form bond with the carbonyl carbon, and it would give me amide, 3 carbon, N, CH3, CH3. Okay, if we have primary amide with 1 carbon nitrogen bond, secondary amide with 2 carbon nitrogen bond, we have 1 carbon nitrogen on this side, 1 carbon nitrogen on the other side. How would you classify this one as the amide? Is it primary, secondary, or tertiary? If you count the number of carbon nitrogen bond or nitrogen attached to how many carbons, we have 1 here, and 1. So this is going to be tertiary. This is ammonia. Let me write again. Carboxylic acid plus ammonia gives us primary. Carboxylic acid plus primary amine, it gives us secondary amide. Carboxylic acid plus secondary amine, it gives us tertiary amide. Okay, so it's like a step up. Very good. So it's like a step up. That's for preparation of amides. Okay. Questions? So what is happening? So let's just follow along this solved problem. It's already solved problem. Is benzoic acid. Leaving group is going to be OH. Nitrogen is a NH2. If it's NH2, then we know it's a primary amine. So if it's a primary amine plus carboxylic acid is going to give us secondary amide. So this is a secondary amide. Okay. I'm not talking about the mechanism of the reaction, but I'm saying overall hydrogen from nucleophile with the leaving group, it gives us byproduct. The byproduct would leave. And then the rest of the nucleophile is going to form bond with the carbonyl group. So we have secondary amide coming from carboxylic acid plus primary amine. If you have any questions, make sure you write in the chat box. I do watch the chat box often to look for the your questions, okay? And your answers. I'm kind of anxiously waiting for those. Okay. In this slide, we have reactions of carboxylic acid. It's not preparation anymore. This is reaction. One of the reactions of carboxylic acid is reduction. For reduction of carboxylic acid, you must use a strong reducing agent. Can you name a couple other reducing agent? So one of them is, which is in this slide, is lithium aluminum hydride. And this is a strong reducing agent. Can you tell me a second one? A reducing agent? Sodium borohydride is weak reducing agent. Wolff-Kishner, that was a strong reducing agent. Clemmensen reduction is a strong reducing agent. but they were specific. They were used to change the CO double bond to CH2. And then you have also H2 with nickel or palladium. So these can be used in any reaction. It depends on you need weak or strong, but and if you want to keep the CC double bond, alkene or alkyne, you would use weaker oxidizing agent. If you use H2, it can reduce all, it would saturate all unsaturated bonds. Let me put an example here to make sure that you remember or you understand what I mean. Let's say if I have cyclohexanol and I add sodium borohydride. Sodium borohydride can only reduce aldehydes and ketones, cannot reduce carboxylic acid because it's weak. Secondary, the ketone would change to secondary alcohol, but the pi bond will stay. If I use H2 with platinum, it would change the ketone to secondary alcohol, and it will also saturate the carbon-carbon double bond. This is not a typo. The double bond would get saturated as well. So it's kind of stronger than sodium borohydride. Lithium aluminum hydride is strong enough to reduce carboxylic acid. You cannot use hydrogen or sodium borohydride to reduce carboxylic acid or acid derivative. You must use lithium aluminum hydride. And if you use lithium aluminum hydride, it would give you primary alcohol because it can reduce. Reduction meaning adding hydrogen, removing oxygen. Lithium aluminum hydride is strong and it can do two-step. So it's going to, first of all, it changes carboxylic acid to aldehyde and then aldehyde to primary alcohol. So it does two-step reduction. Any carboxylic acid derivative plus LAH would give you primary alcohol, except for amides and nitriles. Amides and nitriles, they would give amines. Okay, so let me with acid chlorides. Okay, we have acid chloride here. What happens if you add LAH? Lithium aluminum hydride. So if you add lithium aluminum hydride, it will change to ROH, primary alcohol, which is the primary alcohol. Aldehyde is like somewhere in between. So if you start with the acid, aldehyde, alcohol. This is the most oxidized. And alcohol is the most reduced. And after the alcohol, you can use alkane. Alkane is the most reduced one because you remove all the. With sodium borohydride, you can't go from alcohol to alkane. If you want to go from alcohol to alkane, you have to first do dehydration and then do hydrogenation. So from alcohol to the alkane, first you have to change to alkene. Then you use H2 platinum to go to alkane. You cannot go directly. But alcohol is the least oxidized, carboxylic acid most oxidized. Now, what about the aldehyde is somewhere in between. Now, if you have acid or acid derivative and you want to change it to aldehyde and you don't want to go to primary alcohol, if you want to go primary alcohol, it's easy. From acid to primary alcohol, just use LAH. LAH, That's the abbreviation for lithium aluminum hydride. It's the same thing. But if you want to keep it in aldehyde, you have to be careful. You have to use poisoned LAH. Now, how do you poison LAH? Instead of using LAH that has 4 hydrogens, you take 3 of those hydrogens and replace it with alkoxide group. So like T-butoxide, you replace 3 of the hydrogen with alkoxide or T-butoxide specifically, and you only have 1 hydrogen that can act as reducing agent. LAH, lithium aluminum hydride, has 4 hydrogens that can reduce. But when you poison, you keep only 1 hydrogen and replace 3 of them with bulky alkoxide. Only 1 hydrogen can reduce. So the reduction step is going to be limited, and it will stop in the reduction would stop in the aldehyde position, and it doesn't go all the way to alcohol. The opposite was true, and you saw this before, and we talked about oxidation. If you want to go from alcohol to aldehyde, you would use PCC only. You cannot use a strong oxidizing agent, right? But if you want to go from alcohol to carboxylic acid, you would use sodium dichromate, H2SO4. So from alcohol to acid is 2-step oxidation. From aldehyde to acid is 1-step oxidation, but you need a strong oxidizing agent. If you want to do reduction, if you're going from acid to primary alcohol, you can use LAH directly. But if you want to stop an aldehyde, you must use poisoned LAH. So in this case, you are using Li, and then the poison one, OCCH3, 3 and H. So basically, instead of the 4 hydrogen, you are using only 1 hydrogen to stop in the aldehyde step and don't go to all the way to primary alcohol. Next type of reaction, unless you have questions. If you have any questions, I will answer your question. Otherwise, I would cover the next reaction type. Next reaction is preparation of ketone from carboxylic acid. And for this reaction, you must use Gilman reagent or alkyl lithium. If you use alkyl lithium, one of the R groups is going to replace in alkyl lithium, what happens in alkyl lithium? Alkyl lithium is basically R with the negative, and then Li is a positive charge. So this part of the molecule is acting as a nucleophile. You already have a leaving group here. So this is a substitution reaction. Nucleophile comes in, leaving group would leave, and then you replace the R, which is the nucleophile, with the OH. You replace it with the OH. And you get ketone as a product. Okay. So if you use alkyl lithium with carboxylic acid, you end up with ketone. To prepare acid chloride, the reagent that you are using is thionyl chloride, which is like SOCl2, or oxalyl chloride, C2O2Cl2. Thionyl chloride or oxalic chloride would change the acid to acid chloride. Acid is more stable, is less reactive. Acid chloride is more reactive. Why is more reactive? Because chloride is better leaving group. So for any SN2 type reactions or substitution reactions, acid chloride is going to be a lot more reactive. In general, acid chloride is a lot more reactive. You're going from a more stable reactant to more reactive product. You have to spend more energy. Definitely is endothermic type reaction. And this is like expensive process. And that's why acid chloride is more reactive and is more expensive than carboxylic acid. But the reaction is faster reaction. Carboxylic acid plus either thionyl chloride or oxalyl chloride can give you acid chloride. Acid chloride can do exact same reactions or any reaction that carboxylic acid can do, acid chloride could do much faster. So if you have acid chloride and you add alcohol, what would you get as a product? Acid chloride plus alcohol. You would get ester. We had a whole page with everything that you can get ester. And one of those reactions was acid chloride plus alcohol. Okay, this is just a sample reaction. But in preparation of the acid chloride is just carboxylic acid plus either thionyl chloride or oxalyl chloride that gives you acid chloride. And if you have acid chloride, you can change it to amide, you can change it to ester, you can change to acid chloride, acid anhydride. Okay, here are other examples of reactions of acid chloride with amine is a primary amine. Okay, you have acid chloride and primary amine. We are going to look at the pattern, see if it works. A hydrogen from nucleophile with the leaving group is going to give us a byproduct. And then we have the rest of the molecule would attach to the carbonyl. This is a primary amine plus carboxylic acid. The amide that is formed here is going to be secondary amide. This is a good question for your exam, good question for your quiz, so be prepared to be able to answer a question like this. And in order to do this, you must memorize all your reagents. So what you get in the exam, you would get a diagram like this. Maybe you have the central molecule or you don't have it, but if you don't have it, two of these would be given, so you can actually relate and be able to solve the puzzle. But if this reaction is the central molecule is given, like what happens if you reduce it with poison? So this is like diisopropyl aluminum hydride. That is poisoned reducing agent. With the poison reducing agent on both sides, you will get aldehyde. It doesn't go all the way to carboxylic acid. So you need to learn and memorize your reagent. So if you know that this is a poison, LAH, it will stop in aldehyde. But if you use LAH, it will go to primary alcohol. If you have primary alcohol, if you use sodium dichromate and sulfuric acid, it will go all the way to carboxylic acid. So your exam question, partial, it could be not complete. It can be, just the left side or right side, or a couple of these selective reactions. Either you have the reagents and you don't have the product, the boxes are empty and you have the reagents, or the boxes have the structure formula for the product and the reagents are missing. So in order to answer the questions like that and every other questions, you need to memorize your reagents. This diagram, it shows also starting with the acid anhydride. Acid anhydride is another acid derivative. Remember I said if you have acid derivative, you add water, it would change to carboxylic acid. If you have acid anhydride and you add alcohol, it would change to ester. Acid anhydride, because it's acid derivative plus ammonia, it gives you primary amide. Acid anhydride plus primary amine will give you secondary amide. Acid anhydride plus secondary amine would give you tertiary amide. Acid anhydride can be reduced if you add LAH or lithium aluminum hydride. If you reduce it with that, it would change to primary alcohol. Acid anhydride, if you use poisoned reducing agent, it will change to aldehyde. Acid anhydride plus Grignard reaction. Grignard is a nucleophile. When nucleophile comes in, leaving group would leave. And with second mole of we have to use excess of Grignard. With the second mole, we talked about this in chapter 10 and chapter 11. If you have carboxylic acid, you have acid derivative ester or acid chloride, 2 moles of Grignard reagent would give tertiary alcohol. Acid chloride plus Gilman reagent, it would stop in ester. I'm sorry, ketone. Chapter 18, we talked about the Gilman reagent versus Grignard. Grignard is stronger nucleophile or more reactive nucleophile. It would go all the way to tertiary alcohol, but Gilman would stop in the ketone position. To prepare acid anhydride in industry, they dehydrate acid. That's what the name says, right? Acid anhydride. You move water from 2 molecules of carboxylic acid. Let's say if you have CH3COOH and you have CH3COOH minus H2O. What is minus H2O? Is basically removing H from one and OH from other one. That's minus H2O. And then you get a new bond here. And that gives you the functional group for the product, which is acid chloride. So you have CH3CO, O, CO, CH3. If you write in one line, it's going to be CH3, CO, O, CO, CH3, and is known as acid derivative. Okay, any questions for me? You do? Okay.